Hi everyone. Better yet, I should say good morning, good afternoon, and good evening, depending on where in the world you are watching this from. My name is Muzammil, and I am a technical manager at Cemex UK. And today I'll be talking to you about calcined clays from UK sources. Before we get into that, two main problem statements I'm sure we are all familiar with. Why do we need to make concrete more sustainable? And how exactly can we make concrete more sustainable? The drivers to reduce the carbon footprint are rather well known. Concrete does seem to get quite a bit of bad press, which I believe is a bit unfair. But in fairness, we do use an awful amount of concrete, and as a result, we use an awful amount of cement, which generates considerable amount of carbon. 4 billion tons of cement produced worldwide, generating 23% of global industrial CO2. So how exactly can we make concrete more sustainable? What's being done about it? The use of waste-derived fuels, alternative fuels in clinker manufacture have facilitated CO2 reductions. Advances in technology and with most new cement kilns or modern cement kilns, they're already near thermodynamic efficiency. You can't make them any more efficient. Carbon capture technologies are quite promising, but they're still quite expensive. Some are, in fact, still under development. Ultimately, they're not widely deployed just yet. Non-potent cements such as alkali activated binders or geopolymers uh, have immense potential, but lack of building codes and data on long-term durability limit widespread use. Clinker substitution with SEMs from industrial byproducts, in particular GGBS and fly ash, uh, is still a widely used and an effective approach to cut carbon emissions by 30 to 40% without considerable changes in strength, durability, and costs. The main issue, as we know, is that both slag and fly ash are only available in rather limited quantities. Clays, on the other hand, are naturally abundant, and in many parts of the world, alternative SEMs from calcitic clays are being developed at scale, including limestone calcined clay cements, known as LC3. Although calcitic clays are typically found in tropical and subtropical regions, the challenge with UK-based clays is that calcitic clays are less common here. In such regions, mostly clays comprise of uh, mixture of clay minerals, including halites, chlorites, smectites, and mixed layer clay minerals. It's worth noting that studies on calcined, halite, or smectite are limited. Nevertheless, earlier studies have shown us that calcined calcitic clays are considerably more reactive than calcined smectite or halite, with mixed layer halite smectite clays being least reactive. Of course, one of the main challenges with multi-component clays is the trade-off between optimally calcining certain clay minerals versus suboptimally calcining others. Okay, so this map basically shows the locations of quarries, 5 quarries, where we sourced 5 different clay samples from. The expected clay formation of the samples is highlighted in table 1. It's worth noting that 2 of the samples belong to the same parent group, the Ancombe group, and 3 belong to the Lias group. Okay, so we carried out XRD of the rock layers to identify the minerals present and the associated minerals present. And apologies, we couldn't get hold of one of the samples in time, uh, which basically meant the diffractometer eventually got really busy and outbooked, and so raw clay M5 is missing from this data set. But broadly, the 4 samples, raw clay samples displayed here, showed similar mineral makeup, with kaolinite, morenonite, and alite as the clay minerals. And the associated clay minerals were identified were quartz, calcite, pyrite, traces of dolomite, and gypsum. Right, we carried out thermogravimetric analysis on the rock clays, which basically corroborates the mineral phases identified in the XRD patterns of the rock clays. Mass loss in the temperature range 400 to 600 degrees Celsius for all 5 rock clays is concurrent with the presence of kaolinite. Then you have the mass loss between 600 to 800 degrees Celsius, which can be attributed to carbonate minerals, including calcite and or dolomite. One thing you'll notice is the total mass loss at 1000 degrees range between 11 to 18%, depending on the clay, highlighting the differences in quantities of the minerals present. But basically, based on these findings from XRD and TGA, the calcining parameters were decided to be 800 degrees Celsius peak temperature for residence time of 1 hour to drive the dehydroxylation and amorphization of both 1:1 and 2:1 clay minerals, and to fully decompose pyrite, but we wanted to limit the decomposition of carbonates. Okay, so these are the differential mass loss curves, and of both the raw clays and calcined clays. Immediately you can spot that that the characteristic dehydroxylation mass loss between 400 and 600 degrees Celsius, which was present in the raw clays, was not observed in the calcined clays, which is concurrent with the dehydroxylation of kaolinite. Some dehydration was noted up to 250 degrees in the calcined clays, which is expected because we have observed 2:1 clay minerals in the XRD patterns of the raw clays, and we know that these dehydroxylate at temperatures higher than 800 degrees Celsius. In fact, alite is known to persist from complete dehydroxylation at temperatures up to 900 degrees Celsius. One thing you'll pick up on is the intense mass loss observed between 800 degrees Celsius and 1000 degrees Celsius for clay M5 highlighted by the two peaks centered at 900 and 950. These appear to be new phases because no mass loss was previously observed in the raw clays at this temperature. A possible explanation could be the formation of an amorphous transition state between free lime and metakaolin, or possibly other formed aluminosilicates. Okay, so this table basically shows the mineral content estimates of raw clays determined by thermogravimetric analysis, particularly kaolinite and calcium carbonate contents, which ranged between 17 to 22%, kaolinite and calcium carbonate contents from less than 1% to up to circa 13%. See, here we have the particle size distribution side by side against the R3 reactivity of calcined clays for cross-reference. But basically, all the calcined clays were subjected to the same conditions in a ball mill. But some clays are naturally harder to grind than the others. And what we see here is that clay M1800 was the finest of all clays, or finest of all calcined clays, and M2800 was the coarsest. M3800, M4800, and M5800 showed a comparable particle size distribution. The R3 test over a 7-day period showed M5800 to be significantly more reactive in comparison to all of the clays studied, despite having the lowest kaolinite content. But generally, the three clays of the Lias group, M3800, M4800, and M5800, were found to be significantly more reactive than the clays of the Ancombe group reported in the study. However, all 5 clays reported here meet the 90% confidence threshold to be classified as moderately reactive calcined clays. It must be pointed out that no definitive trends were apparent based on kaolinite content and particle size distribution alone. In order to further investigate this, the results of the R3 test are compared against a hypothetical trend line. The latter was obtained through testing the reactivity of bespoke SCM blends comprising of high purity metakaolin diluted with quartz. Through this, it was possible to evaluate the contribution of 2-to-1 clay minerals present in calcined clays on the overall reactivity beyond what would be expected from kaolinite alone. So the figure shows the reactivity potential of M1800 and M2800 is equivalent to a kaolinite content of about 30%. M3800 and M4800 show a slightly higher reactivity potential equivalent to 35% kaolinite, whereas M5800 was equivalent to about 40% kaolinite. However, it must be noted that the maximum kaolinite content for all the raw clays was less than 23%. So accordingly, these findings are very significant given that the reactivity of clays comprising of circa 35 to 40% kaolinite are considered ideal for LC3 systems. Okay, blended cement systems then. We used SEM2AL 52.5N as both the source of clinker and limestone. Mortars were made using 30% and 50% cement replacement with calcined clays, anticipating that the clays would lead to a drop in consistence. A nominal plasticizer dosage of 0.2% by weight cement was used for the control. During the casting of the first blended calcined clay XM2AL sample, a notable drop in consistency was observed. Accordingly, we used super processizer at increasing increments until a flow table spread comparable to that of control was obtained. Obviously, a higher dosage was needed for the 50% blend. These super processizer dosages were then fixed for all subsequent 30% and 50% blends, respectively. The driver was basically to study the strength at a fixed water to binder ratio, but also to have the consistent workability as near close to the reference as possible. Using these fixed super processizer dosages of 1.1 and 1.5 weight percentage highlighted notable differences in consistency for 30% and 50% calcined clay blends, respectively. In fact, an increase in consistency was observed for blends containing calcined clays of the Lias group, as highlighted by the 4 flow table spread measurements. Okay, the mechanical performance of motors was evaluated at 7 days and 28 days at both 30% and 50% replacement levels. The 30% calcined clay blends showed 7-day strengths which were about 10 to 25% lower than the reference, and 50% calcined clay blends were about 30 to 45% lower than the control at 7 days. But notable strength gain was observed between 7 days and 28 days. The strength data partially agreed with the R3 reactivity test. Calcined clays M3 and M5 were found to be the second most and most reactive, respectively, and also performed the best in terms of compressor strength at 28 days at both 30% and 50% replacements. Okay, to summarize then, the reactivity of clays from 5 distinct sources with low kaolinite contents between 17 to 22% was evaluated. TGA and XRD data confirmed the presence of morildanite, NAlite, along with sulfides and carbonates, in addition to kaolinite. It's clear that in mixed clays comprising of both 1:1 and 2:1 clay minerals, the latter can significantly contribute to reactivity depending on the type and quantity. We found that the R3 reactivity test was a good indicator, albeit not always. SEM2AL was intentionally used as both the source of clinker and limestone to demonstrate viability of adopting calcined clays in concrete plants with 2 silo, cement and SCM configuration. Blended motors with 30% calcined clays from the Lias group reached 28-day strengths of nearly 65 MPa, exceeding the control by 15%. Blended motors with 50% calcined clays of the Lias group reached comparable 28-day strengths to the control without notable compromise on consistency. Right, thank you all for listening in. And finally, I must also acknowledge and offer thanks to Professor Susan Banal, Dr. Yuvraj Dandapani, and University of Leeds, where these experiments were carried out.